Okay, we're going to continue on here, chapter 16, finish up the last little bit of it. And last time we really got into acid, bases, pH. Reminder that the pH scale there runs from 0 to 7 to 14, they say. And less than 7 is acidic, above 7 is basic, and on 7 there is neutral. We talked about a few different calculations. We talked about Kw, which is the concentration of H plus times the concentration of OH minus, and that equals 1 times 10 to the minus 14. Again, remember also H3O plus, same deal. We could use that if we have one of the concentrations or the other. So if we have the H plus or the acid part, or we have the hydroxide part, which is the base part of the solution, we could calculate the concentration of each of those and we could compare them. And obviously, if the H plus is larger than the OH minus, then you have an acidic solution. If the OH minus is larger than the H plus, you have a basic solution. And obviously, if they do equal each other, you do have a neutral solution at that point. We talked about calculating the pH. The pH is equal to minus the log of the H plus concentration. There's also a similar scale that measures POH or OH minus minus the log of the OH minus. And again, these two are helpful because if you take the pH plus the POH, it does equal 14. So it does give you some options. Sometimes you may not even have to use KW. You could, if you have the OH minus given to you, you could get the POH, subtract 14, get the pH from it. We also talked about there that if you are given the pH, you can directly calculate from that the H plus concentration. That's the inverse log of the negative pH. Again, as we talked about, when you put it on your calculator, typically speaking, most calculators will kind of pop up a 10 and a caret. You want to make sure you use the negative button, not the subtract button, and that will get it there. We also have POH, which gives you basically the same option. You could get the OH minus directly from it, and that also is the same calculation, the inverse log of the minus POH. Again, a 10 a caret minus POH. Remember that when you're asked, is it acidic, basic, or neutral, there is only one answer for that question. And you should probably always look at, I'll circle it, there it is. So always look at the pH scale, as that is usually the one everybody has in their head. A reminder that very common mistake sometimes people make when they're doing these problems is they will calculate the pH and it'll be above 7. They'll go, cool, it's basic. Then they'll calculate the POH and go, cool, it's below 7. And they'll go, it's acidic, the same solution. So once again, it can only be one of those things. Most people have, again, the pH scale in their head as the POH scale runs opposite. So if you have a low pH, you'll have a high POH. And if you have a high pH, you'll have a low POH. So they do run opposite of each other. Any questions on any of that there? All right, so let's try a few more examples here just to make sure everything works. The pH of the solution is 5.67. What's the POH? Let's just do it all there. What's the H plus? What's the OH minus? Is it acidic, basic, or neutral here? Let's see what you come up with here. We have the pH given to us, and since we're looking for everything, we do have a few options as to what to do. We could get the POH up front, so I might just do that. So remember the POH is going to equal 14 minus the pH, which would be the easiest move, I think. 14 minus 5.67, that's going to get us there 8.33. At this point, you do still have two options, but I'm going to go after the H plus first, since I do have the pH given to me. Again, directly from the pH, you can do the H plus concentration equal to the inverse log of the negative pH. Again, when you punch it on your calculator, it probably looks something like this. Make sure, again, you use your negative sign, not your subtract sign there or button. And if you do that, we get here 2.1 times 10 to the minus 6. A reminder, you do need molarity as it's a concentration. Also a reminder, two decimal places means two significant figures when we give our answer. At this point, it does open up options. You could use KW to get the OH minus, or you could do the same thing with the POH, which I'll do that. So with the POH, that could give us the OH minus directly. Inverse log of negative 8.33. And that's going to get us something that kind of looks like a 10, a caret minus 8.33. And going to get us there a 4.7 times 10 to the minus 9. Again, we do need molarity there as it is a concentration. And again, two decimal places, two significant figures going in that direction. And hopefully we see the pH here is less than 7, so acidic looks like a winner in this case. Any questions on any of those calculations there? Yeah.
When I tried to plug in basically for 5.67 or 8, but getting error.
Okay, so again, remember it depends on your calculator in most cases. So if you have a display calculator, you should hopefully probably have a button top left that's a second or a shift button. You want to then hit the log, which probably has like a 10 to the X above it. You want to make sure you're actually using your negative button, not your subtract button. That's prob. Yeah, no, so you want to definitely go that direction. And then obviously the number in that case. Obviously, if you have a non-display, as we talked about, you want to work backwards. So you actually do want to start with the number. You do then want to make a negative again using your negative button. And then you want to go second or shift and log. And then you should be in good shape on those. Yeah. Other questions? Obviously, as well, on most people's calculators, they probably will maybe give you your concentration not in scientific notation as well. So you might have obviously a bunch of zeros and stuff like that. So just keep that in mind as well. And sometimes on these, you will run out of space on your calculator and they'll round the last number. So sometimes you'll hit a number that's like all zeros and then like just one number at the end. And that's usually a case where it kind of runs out of space and it kind of rounds a little bit. If you put it into scientific notation, you'll see the actual numbers, other numbers and stuff. Any questions on that one there? All right, let's try a few more here just to make sure. That was quick. Let's do the same thing here. pH is 3.14. What's the H plus? OH minus. POH, and again, is it acidic, basic, or neutral here? Okay, so let's take a look. Once again, we have the pH given to us. So since we're looking for everything, we definitely could get the H plus directly from it. We could also subtract 14 and get our POH. So let's just do the H plus first here. H plus is going to equal our inverse log of a negative pH. So again, should look something like this on your calculator, I would imagine. And you'll end up with, we'll go 7.2 times 10 to the minus 4 molar. Once again, 2 sig figs because of the 2 decimal places. I might as well get the POH as well. POH is going to be 14 minus the pH, which will be 14 minus 3.14. Going to give us a 1.09, looks like. I think. In terms of, oh, I'm sorry, 1.09. That's like a 10. I could read scientific notation maybe. Let's see, try that again. All right, so I got me some scientific notation here. So maybe a 10.86 might be better. There we go. And lastly here, you can again use the POH, just like we did before, and take the inverse log of it to get to the OH minus. You could also go classic, if you will, and use KW as well, like we've done previously, if you wanted to go that route as well. They both really should give you the same answer, maybe slightly different depending if you round it just a little bit, but essentially the same number, which in this case should be something like 1.4 times 10 to the minus 11 molar. And once again, you could get that way or that way in that case. Here we do want to look at the pH, which again is 3.14, so that's going to be less than 7, and that's going to be acidic. Yeah. Any questions on any of those there? Okay. All right, let's do this one. Just what it says. Why don't you just calculate the OH minus concentration? All right, so in this case, again, it does tell you what you could get, which is the OH from that. So we'll go right into our inverse log of the negative POH. And again, that's going to be something like this. And that should get us here. Oh, that's a lot of zeros. 1.4 times 10. Looks like 1, 2, 3, 4, 5, 6. It looks like maybe minus 6 molar. In this case, again, 2 decimal places, 2 sig figs here in the concentration. Any questions on how to calculate pH, POH, OH plus, OH minus, any of those things? Okay, then let us talk about the pH of a strong acid or even literally a strong base. And in some cases, you may be given not just a generic sort of concentration like H plus or H3O plus or OH minus, but you may actually be given a formula for an acid or a base. And a reminder that we talked about strong acids, and there's really a list of 6 which will serve you well in this class and other chemistry classes you take. A reminder: hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. Those are basically a list of 6 strong acids. It's a really good list to know, really, because most of the time you can kind of use it for a process of elimination. If it's an acid and it's not one of those 6, then it's most likely a weak acid. So it's a good way to kind of know, if it's a weak acid or not. And what a strong acid like HCl is going to do is it's going to completely break apart in solution. So it's going to completely dissociate in solution. So if you have hydrochloric acid here and it was in solution, it is not going to stay together. It's going to break apart into H plus and Cl minus. Now, if the concentration of this guy was 0.1 molar, in terms of the pH, the important thing here would actually be the H plus concentration in this case. And we talked about it when we talked about solutions and molarity and all those good things, how the concentration of the whole thing relates to ions, and it is a 1-to-1 relationship, which means the concentration of the H plus would also be 0.1 molar because you're basically going to take 1 times that, and it's a 1-to-1 relationship. So really, we do have the concentration of H plus, which would be 0.1 molar. And that would be all that we would need to go into the pH at this point. So we could go right into the pH equation. Now we'll get us a pH of 1, which is acidic in this case. We don't really need the concentration of chloride, but it also would be 0.1 in this case, as well as a 1-to-1 relationship. The good news is a majority of all of these strong acids are pretty much monoprotic, most of them, which means if you know the concentration of a strong acid, you probably already know the concentration of the H plus, and you could just go right into the pH equation or formula with that concentration, and it will give you the pH of that acid. Now, we could also do it for bases. It works kind of the same way. So remember that a lot of our strong bases come from group 1 and 2 on the periodic table. So you got lithium, sodium, potassium hanging right there at calcium, strontium, barium. If you hook up any of these guys with hydroxide, for the most part, that's going to be a strong base. So things like sodium hydroxide, potassium hydroxide, calcium hydroxide, these are going to be really strong bases. And if we did have something, say, like potassium hydroxide, because it's a strong base, much like our strong acid, it is going to 100% break apart into K plus and OH minus in this case. So 100% going to break apart into these ions. Now, because it's a base and we're interested in pH, we do not have H plus present, but we do have OH minus present. And the presence of that OH minus will allow us to get to the POH, and that will ultimately allow us to get to the pH. So if we had the same concentration here, potassium hydroxide at 0.1 molar, it is a 1-to-1 relationship again here with our hydroxide, and that would get us 0.1 molar, and that basically will equal our hydroxide concentration. That again, as I mentioned, could go into our POH minus the log of the OH minus. That is going to give us a POH of 1. And again, if for some reason you thought that was your pH value, it really shouldn't make sense to you because that's a base. And that if you thought that was pH, that is definitely not a basic pH. But we can get to the pH by taking our 14 minus our POH. And that would get us 14 minus our 1. And that would give us a pH of 13, which is definitely basic and what we would expect to happen here with our strong base. So with bases, you kind of do the same thing, especially strong bases, except that you are looking for the hydroxide concentration. That's going to allow you to get to the POH first and then to the pH. Any questions on that? Now, I would say if you come across a formula for an acid or base in this class, it's probably a pretty safe assumption that's going to be a strong acid or strong base, especially in this context, because weak acids and weak bases take a much longer calculation to figure out the pH, and you don't do that until you go to 1B. And 1B, you'll do that pretty much. But here, probably safe if you see a formula of an acid or base to probably assume that it is going to be strong. You basically just get either the H plus concentration from the acid or the correct OH minus from the base. Any questions on that there? All right, why don't you try a couple here? What is the pH of each of these solutions here? 0.025 molar perchloric acid and 0.025 molar calcium hydroxide. Okay, so let's take a look. This is perchloric acid, which again is one of those 6 strong acids. So we know that this guy is going to 100% break apart in solution into H plus and perchlorate here. Again, in terms of the pH, that is our most important guy. And we could see, as I talked about, it is also a 1-to-1 relationship, which means that is going to be our H plus concentration. And once again, that is all we need. So our pH here minus the log is 0.025. And it's like a 1.60 here. Again, 2 sig figs, 2 decimal places in this case. That is an acidic pH, which makes sense as that's an acid. So again, if you got a basic pH here, you definitely screwed up somewhere. Yeah, I messed up. Any questions on that one there? Looking at the bottom, there's no H plus, but there is OH minus, and that is with a group 2 guy. So that makes me think strong base. So this is going to also break apart. And when it breaks apart, we will get a calcium ion, and we actually will get 2 hydroxide ions in this case. And that's quite important in terms of calculating what we need. In this case, it's a 1-to-2 relationship between the base and the hydroxide. So to get the proper concentration of hydroxide, we do need to actually multiply it by 2. And that's going to give us 0.05 molar, which is really our true hydroxide concentration. So in this particular case, because it broke apart into 2 of them, we do need to adjust the hydroxide concentration to get the correct one. Now that we have the correct hydroxide concentration, that's also something we want to remember. It is not the H plus concentration. That's going to allow you to go into the POH first. And by doing that, minus the log of 0.05, and looks like 1.30. Once again, we could get the pH by taking 14 minus the POH. That's going to give us 14 minus 1.30, 1270 pH, which is basic and does make sense. Any questions on that one? I would say probably out of the strong acids versus strong base, probably the strong bases are the only ones you maybe have to worry about the adjustment there on the hydroxide concentration, especially if they were hooked up with somebody from group 2. Most of those strong acids, as we talked about, are monoprotic, which means they have just one hydrogen to give, which means you don't have to worry about any type of adjustment usually on those guys. Any questions on either of those there? So again, if you do see a actual formula for an acid and base in this class, you probably could safely assume it's going to probably be a strong acid or strong base. As you continue your chemistry career, that is not the case. So again, knowing those strong acids and strong bases are good ways to use it as a process of elimination to know if you're dealing with something that's weak versus a strong acid or base. Any questions? Then that brings us to buffers. Good talk. Let's go back and talk a little longer. So a buffer is a solution that resists changes in pH when you add acid or base to it. So a very big misconception people have about buffers is they think it has to be a neutral solution. And a buffer does not have to be a neutral solution. A buffer can be a neutral solution. A buffer could also be an acidic solution. It could also be a basic solution. You could actually make a buffer at any pH you choose. So at any pH you choose, you can make an actual buffer. What a buffer is able to do is whatever pH it starts at, let's just say you made a pH for a buffer or buffer at a pH of 5, just to keep a nice round number there. So your buffer started at a pH of 5. If you were to add some acid to your buffer, it would be able to resist really big changes in the pH. So maybe the buffer would go from a pH of 5, you add some acid, maybe it goes like 4.9, something like that. A very small change in the acidic direction, but it will not go from like a pH of 5 down to like a pH of 2 or 1. You will not see this big giant jump in pH when you add an acid to that buffer. Same thing would happen if you added a base to your buffer. If you have the same buffer that started at a pH of 5 and you add some base to it, you may see the pH move a little bit. Maybe it goes to like 5.1 or something like that. But you will not see a giant jump in pH. So it will not go from like a pH of 5 to like a pH of 10 or 11 or something like that when you add base. And that's different than in a non-buffer solution. You will see a really big jump in pH. Now, how is a buffer able to do that? A buffer is able to do that based on what it is made out of. And it's made out of one of two combinations. One combination that can make a buffer is it is a weak acid and is sometimes referred to as the salt of its conjugate base. The salt just means it's an ionic compound. It's got a sodium, potassium, something like that hanging out doing nothing really, but just kind of there as well. Or you could have a buffer that is made up of a weak base and the salt of its conjugate acid. Now, what are these definitions? These definitions are the Bronsted-Lowry definition that we talked about earlier. And by the way, you cannot have a buffer made up of a strong acid or a strong base. So if you have a strong acid or a strong base in a beaker, you do not have a buffer. Yeah, so a buffer cannot be made out of, it has to be these weak acids or a weak base has to be involved. They both, by the way, do need to be in the beaker to begin with. You got to have both of those things in the beaker to begin with for it to be a functioning buffer. So for example, everybody's favorite buffer example, which is acetic acid and sodium acetate, like you did in that experiment. Yeah. And by the way, when we look at something like this, first off, I know this is a weak acid, and even if I didn't know it was a weak acid, I should know because it's not one of those 6 strong acids. So again, by the process of elimination, it's not hydrochloric acid, perchloric acid, sulfuric acid, hydrobromic acid, hydriodic acid. So it is none of those, so I know it's weak. And this is its conjugate base over here. And this is the salt of its conjugate base. And the salt is just an ionic compound. That actually is a strong electrolyte, sodium acetate, and it would break apart into a sodium ion and an acetate ion. And in terms of the buffer, it is actually this guy right here and this guy right here that make up the buffer. And that again, the only difference between those two is our 1H plus difference, as we talked about with Bronsted-Lowry. The sodium again is there, it's hanging out, it's floating around, it's doing nothing really, but just swimming around. It is basically a spectator ion, it's just kind of hanging out, not doing much. That is an actual base, and like I said, you will oftentimes see that when you talk about buffers. For example, if I had HF and KF, would this be a buffer? What do you think? HF is what type of acid? HF is a weak acid, as it's not one of those 6, so I know it's a weak acid. And KF is really the salt of its conjugate base. The KF is an ionic compound, which means it's going to break apart in solution. And it is actually, in this case, the HF and the F minus difference there. That is the buffer in this case. Again, this is hanging out, but not really doing much. And that's what makes it a salt. But it is there, but it's not really doing much. But the actual buffering part is that weak acid, in this case, the conjugate base. You could also do this with, as I mentioned before, a weak base and conjugate salt. So for example, you could have a buffer like NH3 and NH4Cl. NH3 has no hydroxide on it, which means it's actually going to be a weak base. And this is the salt of its conjugate acid. This is a ionic compound that will break apart into NH4 plus and Cl minus. In this case, the buffer is these two guys together are the buffer component here. That is actually your spectator ion, just balancing out the charge, doing nothing. If you remember, we talked about earlier on in this chapter, the relationship between a strong acid and its conjugate base, or a strong base and its conjugate acid, and the conjugate acid or base is weak if it comes from something that is strong, and that would come from like hydrochloric acid, so it's relatively weak as well, neutral basically. So we can make a buffer out of both of these things. They both need to be in there. So essentially, when you make a buffer, you have a acid part. I'll just abbreviate it like this, an acid part to your buffer. And you have a base part. So an example, HF would be my acid part, and F minus here would be my base part, as an example of those two things. And they both need to be actually in the solution to begin with. So why can you not make a buffer that is composed of a strong acid or strong base? The real reason is, I'll do it here. When you look at a buffer, and we'll take a look at like our acetic acid and sodium acetate buffer. Because this guy is a weak acid, what's going to happen is it's a weak electrolyte. So as we talked about, it will actually stay together mostly when it's in solution. So in this solution, you will mainly have some acetic acid, and you'll have the arrows and everything heading in both directions because it's a weak electrolyte. You'll make some acetate, and you will have some H plus floating around in that solution. It is going to set up this sort of equilibrium, the weak acid. And what that will do is you will now have in that solution, that's your buffer, you will have a acid part, and you will have a base part to your buffer. And that is critical for how a buffer is able to function correctly. You help this out as well by adding some sodium acetate to it. Sodium acetate is a source of acetate. So you're basically bulking up the amount of acetate that is present in that solution by adding some sodium acetate in there together. So because it involves a weak acid or a weak base, it's able to set up this equilibrium. It's able to keep both parts of that in solution. The acid part of the buffer and the base part of the buffer are able to actually remain in solution. Why can't you do that with, say, HCl and Cl minus? That's an acid, that's a conjugate base. But when you try to do that with HCl, HCl is going to not set up an equilibrium. Instead, it's just going to fall apart 100% into here, which means when you go to try to set up your buffer, you're only going to have in that solution H plus and Cl minus. You'll have the conjugate base, but you have no acid part in that solution. And that's why it will not be able to function as a buffer. And that's why you cannot make a buffer out of a strong acid or a strong base. There's no way to keep both things that you need in that solution in the solution, because a strong acid or base is just going to fall apart. But a weak acid or weak base will set up that equilibrium and keep both the acid part and the base part in the solution at the same time. Any questions on that? So how does it work to actually prevent the pH from going crazy when you add acid or base to it? Let's just take a look at a non-buffer situation and talk about what happens. So let's just take everybody's favorite non-buffer, which is water. And that is a non-buffer. And if I took to water, my wonderfully drawn beaker over here, some water, and I took some hydrochloric acid and I dump it into my water, what's going to happen when I do so is that hydrochloric acid is definitely a strong acid, so it's not going to stay together. It's going to completely break apart into ions. And essentially, when you do that, you just added a bunch of H plus to that solution and some chloride, which is not important. But the important part is you just very quickly added a ton of free H plus. So what does that do to the H plus concentration? Well, in this case, the concentration of H plus skyrockets because all it has to do is go for a swim. And because of that, your H plus concentration just changed dramatically. And what you will see is the pH will then drop pretty dramatically as well. And this is where you're going to get that really big change in pH. It may go from like a pH of 5 down to like a pH of 2 in this case, because all you did is just flood the water with H plus. And obviously the pH is calculated, as we know, minus the log of the H plus concentration. As the H plus concentration increases, the pH decreases a lot, and that gives you that really big jump. Now, what would happen if you added base to your water in this case? So if we took our water here and we added some base, like some sodium hydroxide, which is a strong base, that's going to be a source of sodium and hydroxide ions going in for a swim. In this case, it also will, as we've been talking about, completely break apart into sodium ions and hydroxide ions. And again, 100%, that is what's going to happen. So what you just did in this case is you added some sodiums, which is not that big of a deal, but the big deal here is you added a bunch of free OH minuses to that solution. And that is free OH minus, not attached to anything, just went for a swim. And what that's going to do is basically your OH minus concentration is going to spike up really high because you just added a bunch of OH minus really quickly. The result of that is because OH minus and H plus are tied together, the H plus concentration will then drop really quickly as well. The result of that increase in H plus, decrease in H plus, and increase in OH minus, we'll see your pH start to skyrocket basically in this case. And it will go maybe from a pH of 5 up to like a pH of 10 or 11 because you have just a ton of OH minus in that solution. Kind of back to KW, you got more OH minus than you do H plus. So it's going to become really, really basic at that point. And that's what you're going to see. That, by the way, right, is what happened when you took your beaker of water and you added 1 or 2 drops of your HCl, and the color of the indicator changed really quick, right? Which is like 1 or 2 drops, right? And that's because it has no way, basically, of handling the influx of H plus that you do when you add an acid, or OH minus when you add a base. Question on that there. So then let's talk about what happens when we add the exact same acid and base to a buffer. So let's just do this buffer because I don't feel like writing acetic acid, so we'll just be different. We'll do HF and a little sodium fluoride. This again is my buffer. This is a weak acid and its conjugate base. And once again here, it is not the sodium that's the important thing here. It is the fluoride with the HF. That is the buffer components right there. Whoops. Basically, my F minus is the base part of my buffer, and the HF is my acid part of the buffer. And again, the difference between those is what we talked about, the Bronsted-Lowry difference, just a single H plus. So that is the only one. Again, as you can kind of see here, sometimes you do see some spectator ions in there, and sometimes people get confused when they see like the sodium and stuff like that. Honestly, in most cases, if you're dealing with a buffer, if you got somebody from group 1 or even group 2, really, you could just cross it out. The other thing is really the buffer part. If you have a weak base as your buffer, its conjugate acid will probably have a negative ion from group 7, like chloride, bromide, something like that. And you can get rid of that as well. So you will sometimes see the spectator ion hanging out on the base part or the acid part, depending on your buffer. But really, the acid should always have one more hydrogen, and this guy has one less hydrogen, right? Because it needs to donate the hydrogen. So what happens here in this case is we have our beaker over here that has our buffer in it. And because that is a weak acid, it will set up this equilibrium, weak electrolyte, and it basically will produce both of these guys in solution. You're going to help it by adding some fluoride in there as well. Once again, we have our acid part of our buffer and our base part of our buffer. So now what we're going to do is we're going to basically add some hydrochloric acid here to this. So we're going to take some hydrochloric acid, and that again is a source of H plus and Cl minus. So when I add hydrochloric acid to this buffer, it's going to react with one part of the buffer. Now, since hydrochloric acid is an acid, you could probably guess it should react with the base part of the buffer, right? Because they're called acid-base reactions, right? Not acid-acid reactions or base-base reactions. So when we dump this in there, it's actually going to react with the base part of the buffer, which if you want to leave the sodium in, you can. You can take the sodium out. It don't really matter. But what it's going to actually give you is a double displacement reaction, right? We got positive, negative, positive, negative. We're going to switch some partners going on here, right? And we're going to form on the other side HF and sodium chloride. So what just happened here? Well, we added some strong acid to our buffer. We actually made part of the buffer. So HF is part of the buffer, and we actually made part of the buffer. And that always happens. So because the buffer has two parts, an acid part and a base part, in this case, we used some of the base part of the buffer, but we actually generated some of the acid part of the buffer. And that always happens. You always generate kind of the other part of the buffer. That's why over a long period of time, it can kind of resist changes in pH because you're kind of regenerating part of it as you're doing it. We also made sodium chloride, which is actually a neutral salt. It's not going to really affect the pH or anything like this. But it is actually what we don't see here that we did see when we added this acid to water. And if we take a look at that, when we added the acid to water, what we generated was a bunch of free H plus by itself, not attached to anything, just freely floating around H plus in that solution. And it's that H plus that caused a really big jump in the pH. But when we look at when we add it to the buffer, we don't see any free H plus. And because we don't see any free H plus, the concentration of H plus will stay relatively constant. And if the H plus concentration stays relatively constant, that means the pH stays relatively constant as well. I say relatively constant because if you were monitoring it with a pH meter or something, you would see the pH move, but it would not jump hugely. So again, maybe the pH again starts at 5, maybe it goes down to 4.9 or something like that, but it would not go from like 5 down to 1. So you won't see this really giant amount of jump in the pH. So basically when you add this to our buffer over here, the incoming H plus, which is the problem for the pH jumping, actually will go and find the base part of the buffer. And that base part of the buffer and that H plus will come in and actually create some HF, which is again part of the buffer in this case. The result of creating a little bit more H plus is HF is you will actually increase a little bit of H plus in the solution. And that's why you do see the pH go down a little bit, but not tremendously big jump. Any questions on that? What happens when we do the base here? So if we take our same buffer and we got our HF in there, which is our acid part of our buffer. We got our H plus from there, and we got our F minus, which is our base part of the buffer. And in this case, we're going to add some sodium hydroxide in, which is a sodium ion and a hydroxide ion as the source of what's coming in. So in this case, when we add our sodium hydroxide to our buffer, because sodium hydroxide is a base, is going to react actually with the acid part of the buffer. So bless you, it's going to react with that acid part of the buffer, and we're going to get a regular acid-base reaction, also a double displacement reaction, right? We're going to switch some partners. That's going to make NaF and some water. So once again here, we make the other part of the buffer. We make water, which is not going to screw up the pH in this case. And it is, again, the reason we don't see a big jump in pH is what we actually don't see here. So again, a reminder, when we add the sodium hydroxide to water, we made a ton of OH minus. And as we talked about, that increase in OH minus affected the H plus, and that is what caused that really big jump in pH that we would see with the water. And here, there is no free OH minus made. And because of that, the concentration of OH minus stays relatively constant. And because H plus is tied to that, if the OH minus is not really moving, the H plus is basically staying relatively constant. And by default, my pH is going to be relatively constant. So how a buffer is able to resist really big changes in pH is it's a solution that basically has an acid part and a base part. So that when you add additional acid to your buffer, it will be able to handle the incoming H plus and prevent it from being free by itself. It ties it up basically, right? And the result of that is the H plus stays basically the same and the pH stays the same. And the same thing happens when you add a base to your buffer. When you add a base to your buffer, the acid part of your buffer will react and prevent the OH minus from being freely in that solution. It actually gets tied up there making water. And because we don't make a bunch of OH minus in that solution, it's able to keep the H plus concentration relatively constant as well and the pH relatively constant. That is why we cannot have a buffer that's made out of a strong acid or strong base, because you're missing an essential component that you're going to be in trouble when you try to add an acid or base. So for example, where did I have that picture? Maybe here, yeah. So for example, if you have this as your buffer trying to do it and you add more HCl, all you're doing is now adding a bunch of H plus, and it's not going to be able to resist any changes in the pH. Unlike your buffer that you made in the lab, it took, what was it, about 240 some odd drops? I know my students always think I'm joking when I say it's going to take that long. Keep dropping. Yeah, so it's able to resist changes for a long period of time. Question on that there. Now, when we talk about buffers, when you make a buffer, for example, you typically want to make a lot of times your buffer kind of equal concentrations of the acid part and the base part. And when you do that, what happens is as you add acid, as you may know, it will actually react with the base part of the buffer and it will generate, dramatically drawn here, it will generate more acid part and it will use up some of your base part of your buffer. Dramatically drawn there. And same thing will happen here if you add base to your buffer. It will react with the acid part and you will make more of the base part. So you'll make more of the base part of your buffer. You'll react with some of your acid part of your buffer. Now, are buffers always going to work in all situations? The answer is it depends. If you make a good buffer, you have to take into account the acid you're going to add to it, or the base, the concentration of those things, and the concentration of your buffer. There is something known as buffer capacity, which means if you're not careful, you could blow right through your buffer. So for example, if you didn't follow instructions, which nobody would do in this class, but maybe you grabbed the acid and you just kept adding acid. And if I keep adding acid to my buffer, every time I add acid, it's going to basically eat up the base part. And it'll keep eating up the base part, eating up the base part, eating up the base part. And at some point, you'll blow right through the base part of your buffer. And if you continue to add acid, you are now adding a bunch of H plus, and you're going to see the pH jump really quickly. By the way, you did that in your titration, by the way, when you did this titration of acetic acid and sodium hydroxide. This is a titration curve, by the way, and that's what's going on as you're doing your titration. And as you started your titration with the acetic acid, right around here, you actually made a buffer as a result of your strong acid and weak acid and strong base reaction. Your equivalence point was over here. And what happens though is as you continue to add the sodium hydroxide, you just blew right through your buffer. And maybe some of you noticed, not that the pH jumped, but you added like one drop and your thing went from colorless to super dark pink. That is the reason why, because you made a buffer and then you blew through your buffer and you're at that point just adding a lot of hydroxide really, really quickly. And that's why you see your pH go up a lot. And that's what changes your indicator because something like phenolphthalein works from 8.3 to 10. So you just jumped your pH on your indicator to the dark, dark pink, even though you just added like 1 drop. So actually, when you did that titration, you created a buffer, you blew through your buffer, and you see that really big change when you're no longer a buffer that's happening as a result of somebody maybe saw, again, just like 1 drop was enough to really change that pH. The same thing would happen over here if we continued to add base. We would continue to eat up the acid part, and we would eventually just be adding hydroxide. And it's at that point you would see a really big jump in the pH because you're doing that. That's also why it's really important, for example, if you made a buffer and your buffer's molarity was like 0.1 molar and you went and grabbed the 18 molar hydrochloric acid and added it to it, you're probably going to blow right through it because your buffer can't handle that much H plus coming in at once. So it's really important the concentration of any acid or bases you're adding and the concentration of your buffer. By the way, when you make a buffer, it will probably never hit exactly the pH that you're looking to make it at. But because a buffer can resist changes in pH, you could actually use HCl or sodium hydroxide and add drop by drop, and you could actually dial in your buffer to the actual pH you're looking for, and it won't change a lot because you literally just drop by drop, you can see the pH change very slowly, and you can actually dial your buffer into the right one. Speaking of drops, why did it take so many drops for your buffer to actually change a pH of 1? It's because they set you up when they made you make that buffer. You got how much of the sodium acetate when you made that? I think it was 25 milliliters, right? But for the acetic acid, you got maybe 5 milliliters, right? So that's your base part of your buffer. That's your acid part of your buffer. So the buffer you made in lab looked like this to start with. You had a ton of base, a little bit of acid. And that's why when you're dropping your drops of acid, there's a ton of base to handle all that. And that's why it took forever for your pH to actually change by that much units. If you started closer to each other, it might not have took 240 some odd drops for you to actually see the pH change. So that's what as well. Any questions on buffers, how they work, how they function? All right, that is chapter 16.